Chapter 21.3, reactions of carboxylic acids. So the first thing we need is a method to convert the carboxylic acid into a more reactive species, because carboxylic acids are widely prevalent in nature and readily available for synthetic chemistry. And the way this is done is through the use of thionyl chloride. And we produce as a product here the acyl chloride. Now, I'm not going to go into all the details of pushing the mechanism, but I want to illustrate one of the intermediates here. First, the structure of thionyl chloride. Thionyl chloride is an inorganic acid chloride. If I replace those two chlorides with OH and OH, what would I have? I would have sulfuric acid. So this is the inorganic acid chloride of sulfuric acid, and it's a highly reactive species. And so it reacts to make an inorganic organic mixed anhydride. It's a mixed anhydride. And because it's this mixed anhydride of sulfuric acid, it's actually more reactive than the acid chloride itself. And so when this reacted, we got chloride out of it. Of course, there's a proton floating around out there somewhere to balance the charge. But I want to introduce for you here that nucleophile attacks the carbonyl. Again, we do not do direct displacement at sp2 atoms. So we have an addition. This produces and I'm going to illustrate the rest of it as Lg for leaving group. That would be this sulfonyl chloride fragment here. And then this lone pair swings down and we kick out the leaving group to get to this product. So we've seen now, what's this intermediate called? Right, this is the tetrahedral intermediate. Okay, so you want to be ready to recognize that in many, many places. All right, so that's the first reaction of carboxylic acids. Second reaction, we're actually going to start with the carboxylates. This is a simple deprotonation. Sodium hydroxide and the carboxylic acid will deprotonate it. We don't want water around for this reaction, so carboxylates are readily available. We react that in the general reaction with an acid chloride, and again in an addition mechanism. So if I put the lone pairs in, we have addition to this intermediate. It's going to give us a tetrahedral intermediate. I'm not going to draw this one, but then you get displacement and we produce the anhydride. So you go draw that tetrahedral intermediate, okay? So that's general reaction number 2. Go look up some problems and see those specifically. There are some there in the textbook immediately after this, or in the end of this section, 21.3. I do want to spend a good deal more time on the next reaction, the Fischer esterification. Okay, the Fischer esterification reaction. In the Fischer esterification reaction, we take a carboxylic acid plus an alcohol. And we produce the ester product. Now notice I drew these arrows as an equilibrium. This is an acid catalyzed process with sulfuric acid. And we will push the equilibrium by having an excess of an alcohol and perhaps some way to remove the water, like a Dean Stark trap or some solid reagent that will pull it out of solution and thus remove it from the equilibrium. Shifting it, what's that Gen Chem term for shifting the equilibrium? Le Chatelier's principle. If we remove the water, the equilibrium shifts. And we can also have, typically the alcohol will be the solvent for this reaction, because this is very useful. For instance, if we wanted to, say, take benzoic acid, add methanol, some H2SO4 in a catalytic quantity, we produce the acid. Oh, sorry, the ester. We produce the ester. Okay. Now, let's look at the mechanism of this. I'm going to put the mechanism up with a simple substrate, just the minimum that we need. Take the carboxylic acid. Again, here's our reaction that we're trying to do. We're going to use methanol. Oh, let me just redraw it. Methanol, we're going to add H2SO4, and we're going to get out the methyl ester. All right, so again, key principles of mechanisms. Under acidic conditions, we produce acidic intermediates, and sulfuric acid is a strong acid, and it will be in equilibrium with protonating the carboxylic acid. This makes it a much better electrophile, and so now methanol will attack that carbonyl in another reversible process. And guess what we made? A tetrahedral intermediate. Recognize these, label them, understand them. Now, this has to undergo a proton exchange. We've done this proton exchange a number of times before. I'm going to do this full detailed one time here in this chapter, but then after that we're going to use the shorthand. So we have some base in here, the counteranion for our acid or water molecule. It doesn't really matter what that base is, and we pluck off that proton. And then we're going to put that proton back on at another position. It doesn't really matter which one of the waters that or hydroxides that I add it to. So there's that proton. We now have another good leaving group, right? Hydroxide's not, under acidic conditions, a good leaving group, but water is. Water is a stable molecule. So we have, again, sort of the equivalent of an internal nucleophilic displacement and leaving group leaving. With that happening, we produce, and I'm going to draw this in a particular way to again highlight for you to be able to easily see the ester. This now has a positive charge on this oxygen. It's a mu oxonium ion. And what do we have left to do? We just need a base to pluck off that proton, and we have a product. Okay. Now, that's the mechanism of Fischer esterification. Again, it's all reversible. This step is just as reversible, and it's all about using Le Chatelier's principle to shift the equilibrium. Now, this is the mechanism for ester formation. It's also the mechanism of ester hydrolysis. Okay. In ester hydrolysis, we'll protonate it. Water will attack instead of leaving. We'll lose protons with having tetrahedral intermediates. We reprotonate on the ester portion and go back. And so in that case, we'll put in lots of water, right? Because here there was a water molecule that we needed to remove to shift the equilibrium. But if we put in lots of water, we go the other way. So by learning one mechanism, we've actually learned two, if you just consider thinking about it going backwards. All right, so that's Fischer esterification. Now, there are two more reactions we want to look at. Here's a general reaction. Carboxylic acids are really readily available. They're inexpensive. And it would be nice to be able to directly convert them to an amide. But we need something to activate this to make it a better starting material, a more reactive species. And we do this with what's called DCC. I'll show you what that abbreviation means in a minute. Again, you can use abbreviations, but they must have chemical structural meaning for you. This will then produce and this is a commonly used reagent and method. For instance, if this amine, and I've just illustrated it generically here, we could, for instance, take acetic acid, and if we had, say, an amino group here with a phenyl, let me get one more carbon in there, because I want it to be a specific. Well, that one is okay. That would be phenylglycine. Okay, phenylglycine. If we had a CH2 group there, it would be phenylalanine. With DCC, we can readily make the amino amide, and of course what we've done here, this is the equivalent of a peptide bond found in enzymes and proteins and muscles that I'm using to move my jaws and larynx and voice box in order to make sounds. Now, DCC stands for dicyclohexyl carbodiimide. Now, a carbodiimide has a carbon with two double bonds to nitrogen. Does that remind you of anything? It's an analog of carbon dioxide, okay? and then it has 2 cyclohexyl groups on it. Okay. So this is highly reactive. I'm only going to do a partial mechanism here. It gets protonated. There's the carboxylate. Now I'm going to abbreviate the cyclohexyls as CY. This is protonated, so it's positive. That makes this an even better electrophile. We then attack here, and we generate another intermediate oops. So this is another kind of anhydride intermediate that makes the carboxylic acid more reactive. And then the amine can attack and displace our leaving group in a mechanism very similar to what we saw here for the mixed anhydride from carboxylic acids using thionyl chloride. Same sort of intermediate. Okay, one last and final reaction here. I think I'll just sneak it up on this little bit of space that I have left. We can take carboxylic acids. If we treat them with lithium aluminum hydride, it's a strong reducing agent. Now you have to be careful. This is an acid. The first reaction is hydride acts as a base and makes H2 gas that comes bubbling out, so you don't want it to overheat and get too hot and become flammable or explosive. But this reduces the carboxylic acid, and I'm going to put in those 2 hydrogens here and here that come from the carboxylic, that come from the lithium aluminum hydride. So I'll show you a way that we might make use of this. If we take benzoic acid, now watch what I'm going to do here. I'm going to change my hydride reducing agent just a little bit. I'm going to use lithium aluminum deuteride, D4, instead of H4. And look what I get, because I understand the mechanism and that the hydrides that attach to carbon come from deuterium, and this one comes from the workup, the one on the oxygen. So that produces then the deuterium labeled benzoic acid. And I might want that to do a study of an enzyme that's, maybe I take this alcohol on and react it further into a larger molecule. But with those deuteriums there, I can do special kinds of studies called isotope effect studies, for instance, or I can look at how an enzyme or something might distribute those deuterium into other places and get insights into the mechanisms of the reactions. All right, so that's 21.3. Lots of chemistry, but it has all that same basic fundamental flavor that we're seeing and saw in the introductory section.